All right, we are just past the top of the hour, so we will begin. Ladies and gentlemen, thank you so much for joining us today. On behalf of AUVSI, I'm pleased to welcome you to today's webinar, bvlos UAS Operations for Medical Organ Delivery. My name is Nathan Hoback. I'm the Engagement Manager at AUVSI. And before we get started, just a few housekeeping items to note. As always, all participant lines will be muted during the webinar. We're recording the program, and a viewing link will be emailed to all attendees along with a copy of Aerial Logic's slide deck within the next week or so. You can now view all our webinars on AUVSI's new learning and engagement platform, AVL. If you're listening to the broadcast and need assistance, please send a note to the webinar leader using the chat at the bottom of your screen. After the presentation, we'll open the session for Q&A. So attendees, you're encouraged to submit questions at any time throughout the webinar using the Q&A button at the bottom of your screen, but questions will only be answered at the end of the presentation. Please note, this is a different box than the chat, so please submit all content questions using the Q&A, which can be found along the bottom bar. So let's get started. I'd like to welcome and thank Kongsberg Geospatial for their support of today's webinar. We're excited to have three excellent speakers with us today. Those speakers are Thomas Jimenez, Market Director of UAS at Kongsberg Geospatial, Ryan Henderson, Founder and Director of Flight Operations at Aerial Logic, and Dr. Joseph Scalia, Vice Chair and Professor of Surgery at MUSC Health Solutions. A bit about each of our speakers. So Thomas manages all aspects of enterprise UAS activity at geospatial experts Kongsberg Geospatial, primarily managing IRIS terminal for bvlos operations, airspace management, and multi-domain situational awareness. Thomas has more than 1,000 hours of applied UAS flight experience in utilities inspection, oil and gas, mining and photogrammetry in the USA, Canada, and Latin America. Thomas is also a manned single-engine aircraft private pilot, certified in both the US and Canada. Ryan is an experienced UAV pilot with a background in both manned and remote piloting. He has participated in a variety of UAV projects, including search and rescue, precision agriculture, and global operational deployments. Notably, Ryan was involved in the first transportation of a transplanted organ via unmanned aircraft and several other pioneering UAV operations. As a founder of Aerial Logic, he oversees flight operations, manages pilot qualifications, and is a leading expert in FAA certification for unmanned vehicles. And finally, Dr. Scalia is a surgeon scientist and entrepreneur who conceptualized, designed, and implemented the first systems for moving human organs by drone. He's pioneered the science of environmental factors as they impact organs in transit. He's published more than 100 articles, chapters, and abstracts, and has given dozens of speeches nationally and internationally. So, as you can tell, we have so much unique and impressive experience and knowledge leading this presentation today. So with that, Thomas, I'll hand it over to you to kick us off.
Perfect. Thank you very much. Thanks to AUVSI as always. Thanks, Nathan, and thanks to my guests. As always, but I'm very excited about today's webinar. Primarily because it's such a, to me, I find that medical delivery in UAS is such a good application for drones for good, but also we've got two very good guests today, so I'm pretty excited about it. I'm going to start, as I do normally, a little bit of background about my company, and then go into a bit more detail about the use case, and then what it is that we did in Maryland. And then I'll hand over to Ryan, then over to the doctor. So we're going to get a lot of perspectives. So starting briefly on my company. So Kongsberg Geospatial, who I work for, our parent company is Kongsberg Norway. So it's a very large company, over 200 years old, involved in a lot of different segments: marine, defense, aerospace, oil and gas, with over 13,000 employees and operating in 4 different business areas. So those business divisions per se are broken up, as you can see on the screen, into maritime, defense and aerospace, digital and discovery. Us, Kongsberg Geospatial, we report to our parent, which is Kongsberg Defense and Aerospace. So then coming down to us, Geospatial, our headquarters are in Ottawa, Canada. Most of our team of 83 people are based in Canada. I myself am in South Florida. We've got some colleagues that are also in Texas, but the majority of the team are in Canada. We're over 30 years old, and we focus within the big scope of our parent company solely on, we're a software company, and we build a situational awareness and geospatial visualization tools, so software solutions. and our products are seen worldwide. So this main focus of what we build, it's quite heavily focused on defense, but not only on defense. The primary tool that we build at Kongsberg Geospatial is a mapping SDK called TerraLens. So we sell this SDK to contractors and suppliers, and they then develop the mapping needs for this specific use case that they're building. So that's the lion's share of what we do at TerraLens is that SDK. And you can see, or that SDK is used in some examples that you see on the screen. In some cases, it's defense, and in other cases, it's involved with air traffic control. Notably, and recently, the one in the bottom center here, remote ATC towers, we've delivered what is today the world's biggest remote ATC towers in Norway to Avinor. So this is the room that you can see here in a town called Bodo in Norway. So TerraLens is used in delivering this system. So we build this SDK to deliver this. Today, there's 11 towers, and we've just signed some more towers on that are controlled from one room in Bodo. And excitingly, a couple of months ago, we announced that we're going to be starting a similar project for NAV Canada. So there'll also be a remote ATC towers project, which we're very excited about, and we'll start getting underway soon. So we've got a lot of pedigree in this airspace visualization field. So then that brings it down to specifically the Iris family of products, which, as Nathan described, I work all the UAS side, and this is very much my family of products. It was originally born from a defense system, the NASAM surface-to-air missile fire control system, which in 2015 we improved, and in 2017 we were allowed to repurpose for the use with unmanned aerial systems. Back then it was in its 1.0. Today we're at 2.6.5, I believe. So it's being evolved over the last years and adapted towards enterprise. And I insist enterprise UAS. It's not something that's used in defense. Very broadly, the family of Iris products is split into four. Terminal, which is what we'll discuss today and what we talk about most of the time. GCS, which is a custom built ground control system. We build these custom for clients, built on the backbone of Iris Terminal. Counter UAS, a space that we're getting into a little more now, where we repurpose the backbone of Terminal, however, apply it to critical infrastructure and protecting a location rather than deconflicting an airspace. And then UTM, in the UTM services, we provide various UTM services as described in the FAA interpretation, such as geo-boundary design, vehicle tracking, conformance monitoring, and so on. But for the rest of the day, we're going to look at Terminal in the bottom left. And very gross overview, the way that Terminal works, it's based on static data, terrains, maps, imagery, detailed elevation data. We then overlay periodic aeronautical data. That's static or dynamic, and I'll explain a bit more of that in a second. We then overlay multiple different sensors. So this is how we get our multiple feeds of third-party aircraft or traffic in the sky. Lastly, our own ship position, and then at the top, collision avoidance is an example of one of the many decision support algorithms that are going on in the background when people are using Iris Terminal. So that touches a bit on, then anyone who's seen these webinars before, they'll be familiar with those decks. Now we're going to talk a little bit about the specific bvlos medical organ delivery. So simply put, the use case is point-to-point medical delivery. We've got very high value assets, in this case, organs. They're time-sensitive cargo, which makes it very useful for the business-to-business, or very practical in the business-to-business drone delivery side. And at the end of the day, the cargo is very fragile. So the organ viability is what's fundamental. And again, I'm really glad we got Dr. Scalia, because he's going to expand on this a lot more. But ultimately, organ viability is the period during which an organ remains functional and suitable for transplant after being removed from the donor's body. So the key in this transport process is to minimize the cellular activity and the damage to it. And this organ viability apparently can range anywhere between 4 hours to 6 hours for hearts, or up to 36 hours for kidneys. Ultimately, they're short time frames and they're valuable cargo. The market, it's hard to discern the market exactly for organ delivery, but the medical drone delivery market, which encompasses all medical drone delivery in 2023, was 1.25 billion, with a compounded annual growth rate of in the 18%. The forecast is it'll be just north of 4.5 billion by 2032. Today, North America's market share represents about 37% of the worldwide share in, and I insist, that's medical drone delivery, not medical organ drone delivery. So the challenges today revolve around logistical issues, the organ viability, which I mentioned before, and high costs. So transporting organs quickly and safely is crucial. They've got a limited viability window. Any delays can basically render them unusable. Logistical hurdles such as traffic can complicate a timely delivery. Poor road infrastructure can subject organs to poor environmental conditions. And I'm looking forward to a little more about what Ryan's going to talk about that, because it was really interesting learning this while we were doing the demos. And then the high costs related to to manned aviation, which is one of the alternatives, or today's alternative, which is widely used. So the opportunity that we have is to find this rapid final mile, and I say final mile loosely, point-to-point transportation. The potential to greatly reduce the damage to the organ versus traditional ground solutions, so exposure to temperature, shock, vibrations, to reduce the cost. So manned aviation obviously requires costly aircraft, crews, which I found very interesting talking to Dr. Scalia. It's not just the aircraft and the piloting crews, but also the medical crews that travel with these helicopters. And then obviously it's quite straightforward, but the environmental impact of a electric or a hybrid UAS is considerably lower than a rotor wing alternative of a helicopter or whatever it may be. And then importantly, what part does bvlos play in this whole picture? Realistically, operating medical drone delivery or organ drone delivery in visual line of sight is unpractical. The distance is at 1 mile, which might be visual line of sight, isn't really relevant when we're trying to move organs between two hospitals. The average distance between hospitals in the US, it varies widely. However, there's a general estimate that the median straight line distance is about 13 miles in between two hospitals. So bvlos is fundamental. It's not just important. Safe airspace deconfliction, cooperative aircraft, non-cooperative aircraft, operating inside Mode C veils are all very relevant, but we basically have to deconflict that airspace so as to provide certainty to other users of the national airspace that it won't be a conflict and it won't be a risk to the other people flying in that airspace or to the people beneath. And then reliable DAA, we're very lucky to work with Echodyne in this project. It's expensive, so we need to try and also address how DAA gets scaled and how operators can use DAA as a service. So that's for another day. So now the last part of my presentation before I hand over to Ryan is to just provide an overview of a bit what we did in Maryland over those couple of days. So this was the 5th and 6th of June of this year in near a town called La Plata in Maryland. We were operating in a Class G airspace. We were inside the DCA Mode C veil. And the partners that were working with us today, Aerial Logic, that's who Ryan represents, and he's going to speak a little more. Velos Motors, they were the providers of the aircraft, which probably Ryan will speak to as well. Peak Connectivity, they provided us the at-the-edge connectivity using both, a mesh of both Starlink and LTE connectivity. And of course, our partners at Echodyne, who provided us with radars so as to have that non-cooperative layer added in there as well. And of course, ourselves at Kongsberg Geospatial. So what did we bring to this? As mentioned, Iris Terminal is what I work on. So what Iris Terminal brings is we get all of these sensors that I've mentioned, we bring them into one single pane of glass, one very clean pane of glass. So we can see our own ship UAS on the monitor. We see all cooperative manned aircraft by ADS-B, and I'll show a little bit what the data flow look like. We've also got our non-cooperative tracks. That could be manned aircraft, unmanned aircraft, birds, which we saw a lot of over those 2 days. Then we've got cooperative UAS in the form of remote ID in its various forms. And then, of course, there's decision support tools, which we use so as to be able to alert the electronic observer of any incoming traffic. Then we've also got our AGL and AMSL transparency, because a lot of these sensors report in AMSL. However, to be relevant to an operator on the ground that's often using AGL altitudes, our system ties those two together. And lastly, we've got our own geo boundaries that we build, as well as those that are ingested via the LANC service. So anyone who's seen my webinars before knows that I love horrible clip art. A little breakdown of what it looked like in the field that day. we were receiving all of our all of our ADS-B traffic via an ADS-B sensor, the ping station, which is manufactured by UAVionics. Similarly, so this is all in the same pane of glass. We also fed in Echo Guard radar, same pane of glass. Those are our local sensors. Our aircraft, which is airborne, we've got own-ship telemetry that's feeding into our system, as well as the onboard ADS-B in receiver that's flying with the aircraft in flight. Both of those tracks are also visualized in our screen. Then from the cloud, we can pull in cooperative UAS traffic in the form of network remote ID, or if we brought a remote ID sensor, a broadcast one, we could have done that. And going back to that air risk portion, we're constantly checking the land service for new airspaces. So if anyone opens with TFR or any other dynamic airspace, the electronic observer, who's the person on the right, is going to be able to see it. So to summarize it, all of those, which are made by many different manufacturers and often would require one screen each. So one screen for the radar, one screen for ADS-B, one screen for telemetry, is combined into one single pane of glass. And this is what it looks like. Shout out to our solutions engineers, Anton and Chris, who you see in the picture. But ultimately, all these little lines that you see here are summarized into the back of this box. Now, Iris Terminal is also deployed in far larger remote operating centers, but this gives you an idea of how it can be deployed in a small way. If we get all those cables going to that one box, we have that one pane of glass, and we can see it all. So what were Chris and Anton seeing? This is an example of what it looks like, and we haven't got much time, so it's a very reduced one. But here is, let me lower the volume. It's very short, we've only got 20 seconds, but here's an example of what a conflict looks like. There's a lot going on here. There's a projected volume from the radar that we see on the left, our own aircraft, the bvlos, and the approach and the potential breach of our well clear boundary on behalf of that November 8257 X-ray aircraft. So this is what the UI looks like. You can see in the bottom left here, this is the projected cone, which is the area that the sensors can visualize. We've got our own ship. On the top left, we've got all of our track listings. And then we got a 3D and 2D viewport, as well as our alerts that occur on the right. I'm not going to go into a lot of detail because we don't have much time, but I'd love to show anyone a demo that'd like to see it. So lastly, or closing up, if you like, for bvlos medical delivery, what does our EO situational awareness interface do? Not an interfact, it's an interface. It allows us to monitor that entire airspace, cooperative manned aircraft, cooperative unmanned aircraft, all the non-cooperative tracks that could get involved or could become a problem in a medical beyond visual line of sight delivery. We've also got the dynamic air risk in the sense that we're monitoring airspaces at all times, and you've got those decision support tools. So what do we have? A deconflicted airspace on one pane of glass. So with that, I want to hand over to Ryan at Aerial Logic, and he's going to carry on, and we'll go back for the questions. And thank you.
Thank you very much, Thomas. I appreciate the swap and fantastic recount of our fantastic project that we had together. I'm going to go ahead and share my screen. I've got a few things I would like to share with you here. All right, fantastic. So first of all, I hope everyone is doing well. My name is Ryan Henderson, and I'm with Aerial Logic. And this endeavor started several years ago, but we're going to focus more on this particular project, which I'll go into a little bit of detail here in just a moment. But before we get further into this, one of our jobs at Aerial Logic is to make utilizing unmanned aircraft, drones, reliable, safe, and productive. And one of the things I like to tell people is that when everything is working correctly and everything is set up and planned out properly, operating drones is actually quite boring. And really, that's how it's supposed to be. But in fear of putting too many people to sleep during this presentation, what I would like to do is offer a quick snippet of video of this particular aircraft flying the mission that we're talking about, and kind of give you an idea and feel of what this looks like and even sounds like. Before I begin that video, I'd like to preface there is sound involved with this video, and I've been told that the sound may have been recorded a little bit loud. So please take this moment to adjust your volumes accordingly. You may not necessarily want to put them all the way down, but if you want to put them about 20-25%, I think that will spare your ears and potentially anybody that's sitting around you. And we're going to go ahead and start that video now. And the first thing you're going to see is the aircraft taking off and launching, and then a little bit of in-air airborne video of carrying the payload around our test circuit. So here we go. Taking off. Okay, now that the video's over, I'll give you one more second to bring your volume back up so that you're able to hear me clearly. I appreciate everybody bearing with me on the sound. And also, in full disclosure, I would like you to know that that last piece of that video was not the onboard of the helicopter coming in from landing, but rather a very, very tiny camera drone that was had the pleasure of following around the larger helicopter as it traversed the sky. A little bit about aerial logic. So myself and my team have been doing these type of research and demonstration flights for several years in a variety of locations and environments. And you know, and I think Dr. Scalia will talk a little more about the very beginnings of this concept. But in the beginning, the idea and thought is that, you know, how hard could this be? They're autonomous vehicles. We're going to take a payload. And in some cases, in particular here, we're talking about the medical side of payload. And you're going to connect it to the aircraft, and you're going to put the programmed flight plan in and press the button, and that's done. And it sends it, goes to the other side, and is delivered. It turns out that doing cargo delivery, and specifically medical cargo delivery, is a lot more difficult than one may think. There's a lot of layers to this. And if we'd kind of like to think of it, you know, like a swan, we've got a beautiful swan that sits on top of the water, and that swan glides gracefully across the water from one area to another area. But what we're not seeing is the complexity, the strength, the turbulence, and everything that's happening below the water. Well, that's kind of where aerial logic comes in. We're taking the multi-layers of complexity as it pertains to aviation from a technical side, a mechanics side, and engineering, as well as a regulatory side, and putting all of these things into their appropriate places in the right way to make this successful. The title of this particular webinar being Beyond Visual Line of Sight lends itself to many of the partners that we brought in. And Kongsberg Geospatial and Echodyne did a fantastic job in bringing their roles, their parts, their components to show how we can be fully aware of our airspace for both cooperative and non-cooperative traffic as we're transiting from one location to another. Now, another piece that I'd like to talk about quickly as it relates to this particular exercise is that the helicopter that you see there, it's an all-electric, very quiet, very smooth, redundant system that is capable of carrying the payload box that you see there. For regulation purposes, the maximum payload weight we're able to carry in that box is 12 pounds, which brings the aircraft's total weight to just under 55 pounds to stay inside that Part 107 limit. Can this helicopter carry more and heavier? Absolutely, yes, it can. And in other parts of the world and different operations, it's doing that on a regular basis today. But for our operation, we're operating at under that 55 pounds. Now, one thing that makes this helicopter a little different is that some very specialized and prototyped accelerometers were created on here to minimize and nearly eliminate all the vibrations from the aircraft. In fact, for those of you in the know, the vibration limits actually were down at close to 0.01 IPS. And for any of you that are in even helicopter servicing and maintenance will understand that 0.01 and below IPS is incredibly smooth. And why is that important? Well, vibration is, of course, not good on the aircraft. It's not good for the autopilot. And I think we can certainly surmise that vibrations are not good for a living organ that is destined to go to a recipient and improve their life or perhaps save their life. So while we've done this demonstration and test in multiple different ways in multiple different areas, this is the first time that we've been able to implement an extremely smooth ride for the payload and understand just how good it can possibly be. So again, all electric helicopter, extremely smooth. We were really excited to do this. It takes a lot of different parties to make this happen. Kongsberg Geospatial and Echodyne, as was mentioned, and bvlos Rotors is the manufacturer of this particular helicopter. It was a great support helping to make this happen. As well as Cooler Vibe Technologies, curator of the accelerometers, and then to further understand the tracking and vibrations that were happening on board the aircraft, a company called 7P Technologies provided tracking solutions and vibration analysis devices to help us to understand what was really happening in the air, because clearly we can't be in the air with it. It's uncrewed after all. So that is absolutely tremendous. So now that we've got, a very good solution, a very viable solution for transporting medical cargo or any cargo for that fact from point A to point B, it's good to know that these are highly scalable and automated systems that can move lots of product at very, very with a very small footprint and very small resources from A to B. And that's what we're here doing as Aerial Logic, getting these things commercialized and into the next phase of service. So I want to make sure that I give plenty of time for Dr. Scalia to fill us in on the last piece. And one last thing, I will say we could never have done this actually without Dr. Scalia and the Medical University of South Carolina and all their funders. They're just absolutely tremendous. I know they believe in us, we believe in them, and we're trying to make a difference in people's lives. And if we can do that with uncrewed aircraft, that's where we're going to keep doing and pushing forward. So again, I'm going to turn this over to the great Dr. Scalia. And I appreciate everyone's time today. Dr. Scalia, over to you.
Ryan, thank you very much for, as well as Thomas, for the in-depth analysis on both the technical and technological aspects of what we're doing here, in addition to what's possible out there in the universe. It's incredible to see so many wonderful both entrepreneurs, innovators, and technologists circle around this idea that we've been sharing now for 4 or 5 years. And it's great to see the field advancing. Indeed, with thinking about organs as an opportunity for shipment with drones, we have a pretty bright future. I want to share that with you now. Many folks may be asking how a transplant surgeon somehow fell into the waters with a bunch of aerospace engineers and drone engineers, but let me reassure you that the need is real. Between 2013 and 2018, we spent a lot of time thinking about how organs, not only how do they move today, but how might they move more efficiently. And then in 2018, with funding not only from the University of Maryland and TEDCO out of Baltimore, but also ultimately through the National Institutes of Health, we began studying what it might look like to move human organs by drone. More on why we did that in a minute. And then between 2019 and 2023, we did the first organ shipments and began sharing ideas around what those shipments might mean for human organs. What does it look like to move an organ by one mode of transportation versus another? And then as we look forward to the next 5 years, perhaps partnering, building, and advancing these technologies into the human space in order to save more lives. The need for this is significant. Human organs are recovered from folks who are donating. That may be at any hospital in the United States, and then they're shipped to one of 253 transplant centers around the United States. And we're really only helping about 10% of the patients that we could be helping with transplant for a number of different reasons, but certainly logistics being one of them. And the value of doing the work is incredible. Transplanting the current list would save $50 billion in costs that those patients currently incur as a result of managing their organ failure. And we think we could increase the total number of organs from humans in the United States by upwards of close to 100,000 if all of the environmental and logistical elements of organ, both donation and transportation, were optimized. Moving organs is hard. More than 50 people touch a single organ as it moves from one of those donor hospitals to a recipient hospital. And those challenges are actually getting worse, not because we're intentionally making it more inefficient, but because we understand more about immunology and how to share organs between donors and recipients. And sometimes that means moving organs further distances. That also adds equity to a system that for a long time was not taking into account a number of different variables, which are now included. And none of the different stakeholders that are in this space, perhaps until recently, were fundamentally focused on logistics, rather, of course, doing the best we can to get the most organs that we can to the most recipients. And so as a result of becoming a sort of somewhat frustrated transplant surgeon, thinking through the complicated elements of moving organs from one location to another in the context of allocation, immunology, patient illness, and all these different things, we asked the question in 2017, why not request an organ sort of on your phone once available and have it delivered autonomously donor to recipient hospital, eliminating all the different inefficiencies along the way so that recipient and transplant surgeon number 2, as shown here on the screen, might be able to do that organ transplant. And does that make sense? And the short answer is it does with bvlos, which is part of the reason that this particular webinar is so important. The mean distance traveled by organs is between 70 and 120 miles. This is for a kidney in most cases, depending on a number of different variables, geography around the United States. 30 to 40% of organs are moving 20 to 50 miles. And why that might not sound like a significant distance, it can represent an enormous challenge in terms of logistics. Multiple couriers and centers and drop-offs and handoffs could be obviated by the use of unmanned aircraft via bvlos. And so we're very close to that, as you heard both Thomas and Ryan sharing, that the technologies that exist today very likely can accommodate runs of approximately that long. Intracity and intra-regional town shipments that are currently inhibited by, for example, traffic and availability of couriers are an obvious area where this could change. Now, some of the distances being traveled by organs are increasing, as shown in here. This is a representation from a national organization that manages organ shipment, and we see that some of these distances have increased, but there's a large left shift on this curve suggesting that drones may have a real opportunity to help patients. Now, why do this? We can generate likely more organs as a result of being thoughtful about logistics, right? We, as we generate safer opportunities, we can have on-time delivery, we can have certainty around organ arrival, which improves workflow, ultimately reduces costs in a touchless environment, which allows us to say yes more frequently, thus allowing us to have safer and safer organ shipment, organ transplantation, and better outcomes for our patients. It was a thrilling event to be able to move that first organ, and lead a team of more than 100 people to get that our patient transplanted, and then subsequently to lead multiple teams in the technology space and transplant to bring this to fruition. Now, some of what we learned, wrapping up this presentation here, some of what we learned in the initial studies were that vibration was a key factor in the difference between organ drone shipment and car shipment. And so that begot the question, what could we learn more about this relationship between external environments and the actual organs themselves? And so, funded by the NIH, we were able to bring on not only Aerial Logic, but as well as Kongsberg, to ask and answer critical questions around how to move organs over longer distances than we had in the past, in this case up to 10 miles for a combined 100-mile shipment, in order to learn how does organ shipment by drone compare with ground shipment or traditional aircraft shipment as far as environmental factors, with a specific focus on vibration. Now, those data are embargoed until they are published a little bit later this year, but suffice it to say, it's an exciting time to learn about how these incredible technologies are going to impact patients down the road. Every patient in the United States ought to have access to a transplant. We need better equity in the healthcare system, and unmanned aircraft are definitely a way to do that. And every organ ought to be moving seamlessly to improve the quality of that organ or maintain the quality of that organ in its shipment. And every transplant team should feel safe with the opportunities to leverage incredible technologies, like some of those that you've heard about today, to save lives in the United States and beyond. Thank you very much for the opportunity to share. I have an incredible series of colleagues that are on this call and beyond, and the world is a better and safer place as a result of these folks coming together. Thank you very much.
That's fantastic. Wow. Thank you all. Thank you, Thomas, Ryan, and Dr. Scalia for that excellent presentation. And we'll go ahead and start our Q&A. I'll now open the session up to audience to ask questions. As a reminder, you may submit a question using the Q&A, which can be found next to the chat button at the bottom of your screen. So type your question, hit the submit button, and away we go. So we'll start off with a question for Dr. Scalia. And Dr. Scalia, this question is, as a transplant surgeon, how did you even get interested in drones? What was it about drones that got you excited for this potential?
Yeah, I mean, there are several. I mean, there was a certain number of different cases. I won't give you any specifics, but waiting for an organ to arrive, it's supposed to arrive at 9:30, only to understand that some number of hours later it was in a different hospital in a different part of the country. And without sort of a network of seamless travel options, that eliminates the opportunity to do a transplant. Now, that's kind of an extreme example. But the notion that we have seamless transportation from donor to recipient hospital is hard, but it's possible. And so the interest was more really around the problem, less the solution, although the solution is certainly a fun one to begin to explore, but rather, oh my gosh, I mean, I have a kidney that's 40 miles away. Why is it going to take me 8 hours to get here? Can't we just ... put it on a drone? And that question led to a series of very cool conversations with aerospace engineers at the University of Maryland, who helped pioneer and design, along with us in the surgery lab, some of the initial technologies that we used, and eventually spun out into a series of different companies. But this is a really important topic, and there's nothing more special than getting to work as a transplant surgeon along colleagues like Thomas and Ryan in spaces that are adjacent but synergistic.
Absolutely. And I think you're right. The value and the why is there and obvious. The questions of the how are important. And speaking to the question of when, I have a question for you, Ryan. When do you see this becoming routine for medical delivery?
So I see for small medical delivery, this happening within the next year. We're very, very close. FAA has made incredible strides when it comes to beyond visual line of sight. There are a lot of applicants right now in the 135 space, which will be necessary to make this happen. And then, of course, we have the other component to this, which is a type certified aircraft. And there are several out there. Of course, one that we really, really look up to being Matternet, who's crossed that hurdle, done a fantastic job with the first type certified unmanned aircraft. And then there are several others that are becoming increasingly close. So there's still a few pieces of the puzzle that are coming together, but we're on that cusp. It is becoming very, very close to happening. And like with anything in aviation, we always take a baby step approach to this. I don't think we're going to be seeing any cross-country deliveries by uncrewed aircraft next year or maybe the year after, but that is definitely the goal. And that is the path that we're progressing towards. And with the bright minds and the fortitude and willingness of our industry, we're making those that path, and we're making the strides that are going to be required to happen. So I see the small medical cargo coming up within probably the next year, and I would see the organ piece of that in the very close years to follow that. Again, getting very, very close. It's an exciting time.
It's a very encouraging timeline. Sometimes when you get into uncrewed systems, the timeline is a little bit too far out for you to think like it's tangible. But I like that timeline. Certainly a timeline that thanks to technology. Question about the technology that Thomas, you were describing. So specifically for the IRIS terminal, does the IRIS allow you to factor in the air risk or ground risk during an operation?
Yeah, we've been working on that increasingly. You know, the terminology of air risk and ground risk is used or has been used earlier on in Europe. Yes, it's something that we've been working with our existing clients on. And we're kind of working backwards based on understanding what they require inside their and then their ConOps around their waivers, around their exemptions, and trying to dial it in a little so that it's useful for them. So the air risk, now we've got our integration through our partners at Aloft. So we pull in all of the airspaces, and like I said, we go and check them every 7 minutes. So we can ensure that if you're operating in an area, within a 7-minute refresh rate, you'll know if there's any new air risks, any new airspaces that have been opened. And in terms of ground risk, we've started overlaying a simple version of population densities, in the sense that you can visualize them and check if you're flying over an area that exceeds the population density metric highlighted in your exemption. The next iteration of that will be that, much like our decision support tools, you won't have to look to see that. Every one of those 30 by 30 meter tiles has a value, and we'll be able to alert if any of your flight path falls in an area in excess of the population density highlighted in your exemption.
That's phenomenal. That's perfect. We'll stick with Thomas for this next audience question. So since you're flying under Part 107, how are you able to use ADS-B in these operations?
When we're referring to ADS-B, certainly in the US and in most parts for now, it's ADS-B in. So we're using ADS-B in order to receive traffic from aircraft that are collaborative, aircraft that are broadcasting ADS-B. We're not, and I mean, maybe Ryan will speak a little bit more about it. At the moment, there's very few use cases in the US where UAS are allowed to broadcast ADS-B. But we're talking ADS-B in for the time being in the US.
Fascinating. I appreciate that. We'll bounce back to Dr. Scalia for this next question. So, Dr. Scalia, this next question is, at the moment, hearts, lungs, and many other organs are moved with the transplant team. How will you be able to transport these organs without the surgeon traveling with the organs? Isn't this a requirement given current regulations?
Yeah, no, certainly not within regulation, but out of practice. What we're noting, and as you saw, I mean, we have very brief slide decks today, but there's been a transition in thinking amongst transplant surgeons as volumes grow around the United States and as we try to scale this therapy, that we are the network of transplant surgeons is leveraging itself to have local recovery of organs and then subsequent shipment without that team. Now, culturally, we stopped moving with the kidneys, shipping kidneys with people some number of years ago. Pancreas was kind of a follow thereafter. Liver is just now sort of entering that same space. And part of the reason for that is that we have a series of very cool new technologies that allow the pumping of those organs to prolong some of the time that they can be out of a body. We also have more trust in the system. We previously developed a technology that was commercialized by a company called Medigo, then acquired by CareDx, that allows us to track organs during shipment so we know where they are. And we have some transparency around both the location and safety of those organs. So it's an exciting time to see technology help us scale knowledge and skill for the surgeon networks around the country to move more of these organs and ideally eventually take people out of the sky and allow those organs to move independently.
Yeah, and I think that was one of the benefits on that, cycle chart you showed there towards the end, to just remove the people from some of that equation. We'll bounce back to Ryan. So Ryan, this next question is for you. How loud and how far can the drone be heard?
So I'm going to assume that we are talking about this particular helicopter. We have multiple different, of course, types of aircraft out there. I'll preface with, I do not believe there's any one perfect drone for all jobs. They're all a specialized tool. It's specialized for the task at hand. However, this particular helicopter, particularly because of the sensors that I mentioned, is quite quiet. In fact, at let's say a maximum Part 107 service ceiling of 400 feet with the slightest ambient noise in the background, even let's say a breeze, a wind, or traffic, so on and so forth, it's barely audible. The aircraft is quite quiet when it's underway. In fact, because of the perfect track and balance of the rotor system itself and all other rotating parts in this particular aircraft, the only thing that's audible is the whir of the twin motors, the twin electric motors that are inside. And that's primarily the cooling fins that are on top of it that you hear. Other than that, this large for a small unmanned aircraft is really quiet as it moves through the sky. It's quite incredible.
That is exceptional. We'll stick with you, Ryan, for our next question. And by the way, audience, keep these questions coming. We love the engagement, and we'll get to as many as we can. So, Ryan, for you, do you have any set landing geometry or infrastructure at the hospitals that you're delivering at?
The answer at this point is no. Are we going to have to come up with a standard for this? The answer is yes. But one of the beautiful things about these small uncrewed aircraft is that they are small. The footprint to operate these aircraft just are tiny compared to manned aircraft and full-size infrastructure. The security requirements are still going to remain. Those are going to be there. But again, the beauty of this is they are small. We can of course, utilize current existing manned infrastructure that's there for, say, a helicopter. But do we need to? No. We could utilize maybe a portion of that. We can have an offset in order to not interfere with our manned aircraft counterparts as they continue to do the important jobs that they do every day. But I also want to emphasize that, again, there are different tools of different types of aircraft that are uncrewed. So as we're talking about very small medical, you may be looking at something that appears to be like a pod or let's say a 10 by 10 foot footprint. Or as we progress and we mature in this space and we begin to carry larger packages for longer distance, it may require a larger something that could be similar to the size of a traditional heliport, or further, a runway of some sort as we get into the much larger category and class of aircraft. So again, small medical cargo, very, very flexible. And I think it really lends itself to being added to existing or new infrastructure at a minimal cost at health facilities around the country.
Thank you. I appreciate that. Next one for Dr. Scalia. So how is the United Network for Organ Sharing engaged with this activity, or how's the community involved with or approving of this kind of activity? It's another way to say that question.
Yeah, no, that's a great question. The national landscape of transplant is actually pretty close knit. 56 organ recovery groups called OPOs around the United States, 253 transplant centers, several national organizations, and increasingly courier systems and recovery surgeons, which is exciting. Everyone plays pretty well together in the sandbox and has an aligned goal around improving the access to human organs as fast and most efficiently as is possible. And we've had an enormous amount of support. You know, I would tell you a lot of innovations struggle out of the gate with adoption, but the need here is pretty clear. And we've had a lot of support. I can't think of a single stakeholder who has been sort of purely either uninterested or anti UAV for the purposes that we're sharing. We have spent a ton of time with the United Network for Organ Sharing, their current and former senior leadership, insofar as understanding what's the possible, what's the art of the possible, what's realistic, what needs to be included now and in the future of aviation, in the shipment of organs. How does this layer in over time? In addition, working with some of the courier groups around the country and certainly some of the more, I would say, innovative organ banks or OPOs. And so a warm reception, very exciting. And amongst my surgical colleagues, you know, we've shared this story in multiple forms, nationally and internationally, in both invited talks and presentations at all of our national meetings, and it stirred up an enormous amount of discussion around what's the surgeon's role in leading not only their surgical teams, hospitals, and local advocacy groups for organ donation, but what's their role in leading improvements in logistical support for movement of organs, where the logistics and the support itself actually impacts outcome. Right? We ought to be at the table. We ought to be working with folks like Thomas and Ryan to say, hey, let's not only lead a research project that helps us understand how organs are affected, but let's work together to build the right ecosystem to make this thing happen for the whole country.
It's good. It's good to hear that there's widespread approval, and also good to hear that the organ delivery community is very close-knit. I feel like it needs to be for something this important. Next question will be for Thomas. So Thomas, your question is, are DAA sensors ground-based, airborne, is it vehicle-mounted, or both?
So in the case of our tests in Maryland, they're very much ground-based, and what we're working with at the moment with clients is based on ground-based. So I'll explain that. So again, we work quite closely, for example, with Echodyne. So whether it's their Echo Guard product, their Echo Shield product, in the proof of concepts that we're doing is building corridors, for example, having two Echo Shields facing each other, and as such, completing a volume of space between two locations that are within the performance range of that sensor. So call it, I don't know, 12 miles, for example. Now that's based on ground-based DAA. The future, I think it'll be promising, and we eventually want to reach the stage where it's onboard DAA. What we've been finding, when I say we, it's more so systems integrators that work with us. Onboard DAA in the shape of, for example, an Echo Flight or a Matrix Space. At the moment, there's a lot of noise on that. A lot of these operations are sub 400 feet. Once you're sub 400 feet, a radar generates a lot of noise, and it's hard to filter that out. Recent exemptions, like the ones from AATI, for example, they got success from onboard Echo Flights, I think it was. However, their ConOps is flying a lot higher. That ground noise doesn't affect them as much. And then you got solutions like Cassia X, for example. But ultimately, yes, we want to get to that point where onboard DAA is reliable and it's functional. At the moment, the problem we have with radar, which I think is the best solution, is that, when I say we have the problem, I insist, it's not us that we don't do that, it's our systems integrators, but this is what they're telling us, that they're having low altitude with radar, generates a lot of noise, a lot of false positives, and it's hard to use that as DAA in its current simple form. But we by all means have routed that DAA traffic down to Iris terminal. It can just get messy.
Gotcha. And actually, Thomas, another question for you about the Iris terminal. So you were showing the own ship location on the Iris screen. Where do you access that location data from? Where's it coming from?
In the case of the Maryland tests, so we can pull it from a number of different places. You can pull it from the GCS, which is what we did there. So you open a sidecar port on in this case, it was ArduPilot, and then we can feed that in. We also can work with C2 link partners, for example, Elsight's Halo or UAVionix' Skyline. So as to pull the location through that C2 link. Well, not quite as precise or reliable. We can also use what the future of conspicuity should be, which is network remote ID. So we can simply have an aircraft as a network remote ID module on board and use that to put a dot in space. It's not quite as reliable at this point. However, we're doing testing right now, this week, last week, 3 weeks ago, with network remote ID modules at our headquarters in Canada, so as to also get those on a screen and start working out how we can separate using those.
Wonderful, thank you. The next question I'll direct to any of you who feel compelled with an answer. This question, what feedback, if any, have you identified from relevant insurance or safety regulators regarding the potential liabilities inherent in this very innovative transport methodology with such high value cargo? So whoever feels,
I love this. I love the initial silence.
Yeah, who wants to jump into insurance? Go for it.
Sure, I'll take a stab at this. So as we all know, we are currently in a research and demonstration phase of this. And at current time, the cargo that we're carrying is no different than, any other commercial flight that we're doing. And under Part 107 rules, we're flying, everything is compliant under Part 107. I do foresee that there is going to be a shift in insurance as this becomes more commercialized and these routine operations become a regular thing. But I would anticipate that, and again, here I am speaking the non-insurance guy. I'm not the insurance guy. I pay a lot of insurance premiums on multiple things. But what we're finding is that it's an aviation policy at the end of the day. And the aviation practices that we're adhering to are the same things, whether it's an uncrewed aircraft or a manned aircraft. We're adhering to the same policies, the certifications, the regulations, and the rules. And all of those things have to match. So I have read various articles that UAS insurance is still trying to find their way a little bit and understand what the risks are inherently between air and ground and equipment. But as we get further into the certification realm of this and more 135 operations, I can't imagine that these will differ too much from a traditional manned aviation operation.
Gotcha, understood. So it's a sort of wait and see. Dr. Scalia, I see you unmuted. Did you have something to add, or?
Yeah, I mean, so there are lots of different ways to look at this bucket, right? Safety matters. In fact, part of the reason that we're doing this is actually safety to begin with, right? Moving organs faster allows us to add some level of safety and quality of the organ being transplanted. And so that there's obviously an interest there. From the standpoint of a hospital, taking surgeons, nurses, technologists, and perfusionists out of the air actually has a much better safety profile than moving their teams, long distances. And so it actually reduces some of the insurance complexity to do this from the standpoint of a hospital or from a surgical practice where your teams are moving around. To that point, there's an added level of safety, although not pure insurance, Nathan, around ensuring that you can have some more certainty around when organ transplants will occur in order to sort of optimize the safety of the surgical procedure itself when you go to do the implant. I think there are a lot of other interesting topics. We actually had a national discussion about exactly this. What are the policies required for surgeons, teams, airplanes, and such when organ shipment teams are moved around the country to recover organs. But I think that's a little bit beyond the scope of today. Suffice it to say that there's interest, there is some implication, and that there may be a small benefit for teams and hospitals.
Agreed. So we are almost to time. So I do want to give each of you about 30 seconds or so each, just to provide a final thought before we depart. We can begin with Ryan, then Thomas, then Dr. Scalia, perhaps.
Sure. Thank you very much for that, Nathan. And again, thank you to all the participants that took the time out of their day to come and listen to our story. I think the big takeaway here is that while we are ever striving to make this a reality, and on the outside, we want to make this as seamless and easy as possible. In the end, it's about improving the quality of life and saving lives. If we can do that, I definitely know that we've achieved our goal. Again, this is the onion and we're peeling back the layers. It takes many organizations and individuals to make these things possible. And, with your support, the industry support, we're going to keep marching forward on this and we're going to see this through to the end. Really appreciate everybody here, your questions. And I look forward to meeting several of you, whether it's going to be at Exponential or some other event. So thanks again. Appreciate it, everybody.
Thank you, Ryan. Quick note to just, again, thank all the attendees. To me, I get to work in a lot of different, with all our different clients, a lot of different spaces. I'm really passionate about this space. I really believe in drones for good. I'm passionate about beyond visual line of sight and about bringing together the industry so as to make bvlos scalable. Like there's a lot of discussion in the industry about DAA, C2, making it affordable so that operators can actually use these things without having to buy them. We need to collaborate before we compete. So I love the use case. I really enjoyed the time out in Maryland. And if anyone has any questions, please send me something through LinkedIn. If not, in about 3 weeks, I'll be in ICAO in Montreal as well. And I'd love to see anyone there as well. Thank you. And over to Dr. Scalia.
I'll close it out to say that many of you in the audience are interested in something that feels impossible. And, we were told many times over the course of the last 5 years that this was either not possible, it was too big, too expensive, or just simply not going to happen. And here it is happening. If you have an idea for something that can change lives and you can find folks that are interested in aligning with that goal, it will happen. And this is a testament to that. Bringing people together from different fields and spaces that are adjacent, but not necessarily normally working together is a great way to do that. Smart people combine together, synergize to come up with great opportunities to innovate. And here we are saving human lives with aerospace engineering and incredible both radar technologies and imaging analysis. And there you go, sort of the proof is in the pudding. So thank you for the support. Thank you for the time. Thank you to all the webinar listeners. And we look forward to taking this to the next level and getting it off the ground.
Well, wonderful. Literally off the ground. So on behalf of AUVSI, I'd really love to thank all three of you, Thomas, Ryan, Dr. Scalia, for today's excellent presentation and discussion, and also to Kongsberg Geospatial for their generous sponsorship of this webinar. So attendees, you'll receive a link to access the webinar recording within the next week or so. Another exciting feature is that all webinar recordings are now available on AUVSI's learning and engagement platform, Able. So when you visit Able to view the recording, please take a moment to look around, visit our active courses, check out archive content in the library, share some industry news and what you're working on in my community, connect with industry professionals, and so much more. When you receive that viewing link, there will be additional information about accessing the recording and also the slides from Ryan in Able. If you have additional questions or comments, please email us at education@auvsi.org. And lastly, today's presentation and program is copyrighted by AUVSI with all rights reserved. Thank you and have a great rest of your day.